The National Electrical Code, or NEC, addresses the installation of different types of conductors. NEC Section 800.180 A2 states that conductors or cables of different types used for transmission and distribution of power shall be installed in separate raceways or ducts. NEC Section 800.180 C states that conductors or cables of different types installed in the same raceway shall be separated by a solid insulating barrier. Although the NEC doesn't explicitly address the separation of high-voltage power cables and fiber optic cables in the same trench, it does require that conductors of different types be separated in separate raceways or ducts. The utility company might believe that their kilovolt line will not be affected by the fiber optic cable because the two cables are in separate conduits and there is no electrical connection between them. The phone company's request for a 1-foot separation is likely based on industry best practices and concerns about potential electromagnetic interference or EMI from the power cable. To address the concerns, firstly, consult with a qualified electrical engineer who can provide guidance on the appropriate separation distance based on factors such as the specific power cable and fiber optic cable used. Secondly, consider using a physical barrier. Installing a solid insulating barrier between the two conduits, as required by NEC Section 800.180 C, can help reduce EMI and provide additional protection. Thirdly, coordinate with the utility and phone companies. Work with both companies to determine an acceptable compromise that meets their safety and performance requirements. The trench design should consider the possibility of future maintenance or repairs to either the power or fiber optic cable. It is important to follow all applicable local codes and regulations, which may have additional requirements for the separation of utility lines and fiber optic cables. Electromagnetic interference, or EMI, is a disturbance caused by electromagnetic radiation emitted from electrical devices or systems that can disrupt the performance of nearby electronic equipment. High-voltage power cables can be a significant source of EMI due to the high currents and voltages they carry. Fiber optic cables are generally immune to EMI because they transmit data using light signals rather than electrical signals. However, the metallic components of fiber optic cables, such as the armor or shielding, can still be susceptible to EMI. If a fiber optic cable is exposed to high levels of EMI, the metallic components can act as an antenna, picking up the electromagnetic radiation and conducting it to the electronic equipment connected to the cable. This can cause interference with the data being transmitted over the fiber optic cable, leading to errors or data loss. The level of EMI generated by a high-voltage power cable depends on several factors, including the voltage and current of the cable, the distance from the cable, and the presence of any shielding or grounding. In general, the higher the voltage and current, the greater the EMI. The further away from the cable, the lower the EMI. Shielding and grounding can help to reduce EMI. The sensitivity of a fiber optic cable to EMI depends on several factors, including the type of fiber optic cable, the quality of the cable connectors, and the distance the data is being transmitted. Some fiber optic cables are more resistant to EMI than others. High-quality cable connectors can help to reduce EMI. The longer the distance the data is being transmitted, the more susceptible the fiber optic cable is to EMI. There are several ways to mitigate the effects of EMI on fiber optic cables. One way is to use shielded fiber optic cables. Shielded fiber optic cables have a metallic shield that surrounds the fiber optic cable and helps to block EMI. Another way to mitigate the effects of EMI is to ground the metallic components of the fiber optic cable. Grounding provides a path for the EMI to flow to ground, which can help to reduce the amount of EMI that reaches the electronic equipment connected to the cable. Another way to mitigate the effects of EMI is to keep fiber optic cables away from high-voltage power cables. The further away the fiber optic cable is from the high-voltage power cable, the lower the EMI. Finally, another way to mitigate the effects of EMI is to use filters. Filters can be used to block EMI from entering the electronic equipment connected to the fiber optic cable. It is important to note that even if fiber optic cables are immune to EMI, the electronic equipment connected to the cables may not be. Therefore, it is important to take steps to protect the electronic equipment from EMI, such as using shielded enclosures and filters. The National Electrical Code, or NEC, provides guidelines for the installation of electrical systems to ensure safety and prevent hazards. While the NEC doesn't explicitly address the separation of high-voltage power cables and fiber optic cables in the same trench, it does provide general requirements for the separation of different types of conductors. NEC Section 300.3 C1 addresses conductors of different systems and states that conductors of different systems shall be installed in separate raceways, cables, or enclosures. One example is where communication, signaling, and low-power circuits are used. Article 725 also provides some requirements. The purpose of this requirement is to prevent the mixing of different voltage levels and current types in the same raceway or enclosure, which could create a safety hazard. High-voltage power cables carry a large amount of electrical energy, which could potentially damage or interfere with the operation of fiber optic cables. Fiber optic cables are used to transmit data using light signals and are sensitive to electromagnetic interference, or EMI. If a fiber optic cable is installed too close to a high-voltage power cable, the EMI from the power cable could disrupt the data transmission and cause errors or data loss. In addition to the potential for EMI, there is also a risk of physical damage to the fiber optic cable if it is installed too close to a high-voltage power cable. If the power cable were to fail or be damaged, it could potentially damage the fiber optic cable as well. To address the concerns of both parties, it is recommended to follow these steps. Firstly, consult with a qualified electrical engineer. An electrical engineer can assess the specific conditions of the installation and provide recommendations for the appropriate separation distance between the power cable and the fiber optic cable. The engineer will take into account factors such as the voltage and current of the power cable, the type of fiber optic cable, the soil conditions, and the presence of any other underground utilities. Secondly, consider using a physical barrier. Installing a physical barrier between the power cable and the fiber optic cable can help to reduce the risk of EMI and physical damage. The barrier could be made of concrete, plastic, or another suitable material. The barrier should be installed in such a way that to provide adequate separation between the two cables. Thirdly, coordinate with the utility and phone companies. It is important to coordinate with both the utility company and the phone company to determine an acceptable compromise that meets their safety and performance requirements. The utility company may have specific requirements for the separation of power cables from other underground utilities. The phone company may have specific requirements for the protection of fiber optic cables from EMI. By working together, the three parties can develop a solution that meets the needs of all stakeholders. In addition to the above recommendations, it is also important to follow all applicable local codes and regulations. Local codes and regulations may have additional requirements for the separation of utility lines and fiber optic cables. It is important to check with the local authorities to ensure that the installation meets all applicable requirements. The trench design should consider the possibility of future maintenance or repairs to either the power or fiber optic cable. The trench should be wide enough to allow workers to safely access and work on both cables. The trench should also be deep enough to provide adequate protection for the cables from frost and other environmental factors. The National Electrical Code, or NEC, is a comprehensive set of standards for the safe installation of electrical wiring and equipment in the United States. It is updated every 3 years to reflect the latest advances in technology and safety practices. The NEC is not a law itself, but it is widely adopted by state and local governments, which make it legally binding. The NEC covers a wide range of electrical topics, including wiring methods, overcurrent protection, grounding, and equipment installation. It is divided into chapters and articles, each of which covers a specific area of electrical work. The NEC is an essential resource for electricians, engineers, and anyone else involved in the design, installation, or inspection of electrical systems. It provides clear and concise guidelines for ensuring that electrical work is performed safely and in accordance with best practices. The NEC is a complex document, but it is well organized and easy to navigate. It includes numerous tables, figures, and examples to help users understand the requirements. The NEC also includes a glossary of terms to help users define unfamiliar words and phrases. The NEC is an indispensable tool for anyone working in the electrical industry. It provides the knowledge and guidance needed to ensure that electrical systems are installed safely and reliably. The NEC is available for purchase from the National Fire Protection Association, or NFPA. It can also be accessed online through various subscription services. The NEC is a living document. It is constantly evolving to meet the changing needs of the electrical industry. It is important to stay up to date on the latest changes to the NEC to ensure that electrical work is performed in accordance with the most current standards. Underground electrical installations are subject to a variety of environmental factors that can affect their performance and longevity. These factors include moisture, temperature, soil conditions, and the presence of corrosive substances. Moisture can enter underground electrical systems through several pathways, including rainwater, groundwater, and condensation. Moisture can cause corrosion of metal components, which can lead to electrical failures. Moisture can also create a path for electricity to flow to ground, which can cause shocks or fires. Temperature fluctuations can also affect underground electrical systems. Extreme temperatures can cause the insulation on wires and cables to degrade, which can lead to electrical failures. Temperature changes can also cause the ground to expand and contract, which can put stress on underground electrical components. Soil conditions can also affect underground electrical systems. Acidic soils can corrode metal components, while alkaline soils can damage concrete structures. The presence of rocks and other debris in the soil can also damage underground electrical components. Corrosive substances, such as salt, chemicals, and fertilizers, can also damage underground electrical systems. These substances can corrode metal components and degrade insulation materials. To mitigate the effects of environmental factors on underground electrical installations, several measures can be taken. These measures include using corrosion-resistant materials, providing adequate drainage, protecting against temperature extremes, and using backfill materials that are compatible with the soil conditions. Corrosion-resistant materials, such as stainless steel and copper, can be used to protect metal components from corrosion. Adequate drainage can be provided to prevent moisture from accumulating around underground electrical components. Protection against temperature extremes can be provided by insulating underground electrical components or by burying them at a depth where the temperature is more stable. Backfill materials that are compatible with the soil conditions can be used to prevent damage to underground electrical components. In addition to these measures, it is also important to perform regular inspections of underground electrical installations to identify and address any potential problems. Regular inspections can help to prevent electrical failures and ensure the safety of the public. Fiber optic cables are used to transmit data using light signals rather than electrical signals. This makes them immune to electromagnetic interference, or EMI, which can disrupt the performance of traditional copper cables. Fiber optic cables are also capable of transmitting data at much higher speeds than copper cables. Fiber optic cables are used in a wide variety of applications, including telecommunications, data networking, and cable television. They are also used in industrial and medical applications, where their immunity to EMI and high bandwidth make them ideal for transmitting sensitive data. There are two main types of fiber optic cables: single-mode fiber and multimode fiber. Single-mode fiber has a smaller core than multimode fiber, which allows it to transmit data over longer distances with less signal loss. Multimode fiber is less expensive than single-mode fiber, and it is typically used for shorter distance applications. Fiber optic cables are made of glass or plastic fibers that are surrounded by a protective coating. The fibers are very thin, typically only a few microns in diameter. The protective coating helps to protect the fibers from damage and to prevent them from bending too much. Fiber optic cables are connected to equipment using special connectors. These connectors are designed to align the fibers precisely so that the light signals can be transmitted efficiently. Fiber optic cables are relatively easy to install and maintain. However, they are more delicate than copper cables and they must be handled with care to avoid damage. Fiber optic cables are a reliable and cost-effective way to transmit data over long distances. They are also immune to EMI, which makes them ideal for use in environments where there is a lot of electrical noise. Electrical engineers are responsible for the design, development, testing, and supervision of the manufacture of electrical equipment. They work in a wide variety of industries, including power generation, transmission and distribution, telecommunications, electronics, and manufacturing. Electrical engineers use their knowledge of mathematics, physics, and engineering principles to solve complex problems related to electrical systems and equipment. They design and develop new electrical products such as motors, generators, transformers, and electronic circuits. They also test and evaluate electrical equipment to ensure that it meets safety and performance standards. Electrical engineers often work in teams with other engineers and technicians. They may also work with customers to understand their needs and develop solutions that meet those needs. Electrical engineers must have a strong understanding of electrical theory, circuit analysis, and computer-aided design, or CAD, software. They must also be able to communicate effectively, both orally and in writing. Electrical engineers typically have a bachelor's degree in electrical engineering. Some electrical engineers also have a master's degree or a doctorate in electrical engineering. Electrical engineers are in high demand in many industries. The median annual wage for electrical engineers was approximately $100,000 in May of 2022. The job outlook for electrical engineers is expected to grow approximately 3% from 2022 to 2032, about average for all occupations. The increasing demand for electrical engineers is due to the growing use of electricity in all aspects of modern life. The electric power grid is a complex network of power plants, transmission lines, and distribution lines that delivers electricity to homes and businesses. The electric power grid is essential to modern life, and it is constantly being upgraded and expanded to meet the growing demand for electricity. The electric power grid is also becoming more complex as it integrates more renewable energy sources, such as solar and wind power. The integration of renewable energy sources requires new technologies and control systems to ensure the reliability of the grid. The electrical utility industry is responsible for generating, transmitting, and distributing electricity to consumers. The electrical utility industry is a highly regulated industry, and it is subject to strict safety and environmental standards. The electrical utility industry is also undergoing a period of rapid change as it adapts to new technologies and regulations. The electrical utility industry is a vital part of the economy, and it provides essential services to homes and businesses. The electrical utility industry is also a major employer, providing jobs for millions of people. The electrical utility industry is committed to providing safe, reliable, and affordable electricity to consumers. The electrical utility industry is also committed to protecting the environment and reducing its carbon footprint. Utility companies must comply with various regulations and standards to ensure the safety and reliability of their operations. These regulations and standards cover a wide range of topics, including power plant design, transmission line construction, and distribution system maintenance. Utility companies must also comply with environmental regulations to protect the air and water quality. Utility companies are subject to oversight by various regulatory agencies, including the Federal Energy Regulatory Commission, or FERC, and State Public Utility Commissions, or PUCs. These regulatory agencies are responsible for ensuring that utility companies comply with all applicable regulations and standards. Utility companies are also subject to liability for damages caused by their operations. Utility companies must carry insurance to cover these potential liabilities. Utility companies have a responsibility to provide safe, reliable, and affordable electricity to consumers. Utility companies must also protect the environment and comply with all applicable regulations and standards.